Welcome to Creative World. In this video, we will solve chapter 2 exercise problem number 2.10. Read the scenario. Determine the voltage across each diode in given below figure. Using diode complete model with dynamic resistance of 10 ohm and reverse resistance of 100 mega ohm. This figure contains 4 circuit diagrams. A silicon-based diode is connected in different configurations in each circuit diagram, and we have to find voltage across this silicon-based diode in all of these circuit diagrams. But this time we have to consider diode complete model. In this case, if a diode is in forward biased condition, it will have a series resistance which is known as dynamic resistance. While if the diode is in reverse biased mode, then it will act as an open switch and it will have a reverse resistance across its terminals. So without wasting time, let's proceed towards the solution of this problem. We will start from figure A. In this circuit diagram, a diode is connected between two voltage sources through a 10 ohm resistance. Negative of both voltage sources are grounded, while the positive 8 volt is appearing on the cathode of diode. On the other hand side, the anode of the diode is connected to positive 5 volt. So first we have to identify the biasing of diode. Either it is forward biased or reverse biased. In order to do that, we will find the voltage difference between its anode and cathode terminal. So positive 5 volt is appearing on its anode terminal and positive 8 volt is appearing on its cathode terminal. Now find the difference of voltage, that will be equal to 5 volt minus 8 volt. It will become minus 3 volt. So minus 3 volt is appearing across this diode. This minus sign is indicating that the value of cathode voltage is higher than anode voltage. Now recall the conditions for the forward biasing of a silicon based diode. The third condition was that the anode voltage should be higher than cathode voltage. But here this is the opposite case. Anode voltage is lower than cathode voltage. So this diode will be acting as an open switch, or we can say that this diode will be in reverse biased mode. After identifying the biasing of this diode, now we have to consider complete model of diode and find voltage across this model. We know that in case of reverse biased diode, the diode acts as an open switch and a reverse resistance is connected across its terminal. In this case, the value of this reverse resistance is 100 mega ohm. So this is the complete model of a reverse biased diode. We have to find voltage across its terminal. Now we have to find voltage across the terminals of this diode. We know that the potential difference between these 2 points is minus 3 volt, and we have to find voltage across this resistance. So we can use voltage divider rule because these two resistances are connected in series connection, and voltage divider rule will be utilized to find voltage across this resistance. So voltage across this resistance will be equal to 100 mega ohm multiplied by voltage difference, that is minus 3 volt, divided by the sum of both series connected resistances, 10 ohm plus 100 mega ohm. Now solve this equation. Voltage across this resistance will be equal to minus 2.99 volt, and actually these voltage will be appearing across diode as well because of parallel connection. So we can say that in this diode complete model, we will be having minus 2.99 voltage across it. Move to the next circuit. In this circuit, a diode is connected through a resistance of 560 ohm to a voltage source. Positive terminal of this voltage source is connected to the anode of the diode, while negative terminal of this voltage source is connected to the cathode of the diode. So this diode is in forward biased mode because the positive terminal of voltage source is connected to anode and negative terminal of voltage source is connected to cathode, and potential difference of this voltage source, which is 100 volt, and it is much higher than the potential barrier of this silicon based diode. So we can say that this diode is in forward biased mode. Because this diode is in forward biased mode, so it will be having a voltage difference across its terminal, which is also known as potential barrier or forward voltage drop of diode. As we are dealing with silicon based diode, so this voltage will be 0.7 volt. We can say that 0.7 volt with this polarity will be appearing across this diode. Now we have determined the voltage across this diode, and we also determined the biasing of diode. As we discussed earlier, if a diode is in forward biased mode, it will be having a resistance connected in series to it, and that resistance will be known as dynamic resistance of diode. Here I have included the complete model of diode, which have a potential difference across its terminal of 0.7 volt and a dynamic resistance connected in series connection to it. Value of dynamic resistance is 10 ohm. Now we have to find voltage across the complete model of diode. So in order to do that, we should have the value of voltage across this dynamic resistance. That can be calculated using voltage divider rule again, because this resistance and this resistance are connected in series connection. And we know the supplied voltage, so we can apply voltage divider rule to find out voltage across this 10 ohm resistance. In order to do that, first we have to subtract the forward drop of diode from supplied voltage. Because this voltage are being dropped from this supplied voltage, the remaining voltage will be appearing across these two resistances. So the remaining voltage will become 99.3 volt. Now our potential difference across these two resistances will be equal to 99.3 volt. And we have to consider this difference of voltage as supplied voltage. So voltage divider equation for this resistance will be 10 ohm multiplied by 99.3 volt divided by 10 ohm plus 560 ohm. Solve this equation to find out voltage across this 10 ohm resistance. That will become 1.742 volt. After calculating voltage across this dynamic resistance, now we have to find voltage across this complete model. In order to do that, we will add up these two voltages because these are connected in series connection. So complete model of diode will be having voltage across its terminal 2.442 volt. Move to next circuit diagram. In this configuration, a diode is connected parallel to a series voltage divider network through a resistance of 4.7 kilo ohm, and we have to find voltage across the complete model of this diode. So in order to apply the complete model, first we have to determine either this diode is in reverse biased or forward biased. In order to do that, we should have the value of voltage across these points, because whatever the value of voltage that will be appearing across this 4.7 kilo ohm resistance, those same voltage will also be appearing across this series connection of diode and resistance because of parallel connection. So first we will calculate voltage across this 4.7 kilo ohm resistance. In order to do that, we will omit these two elements from the circuit for now. The circuit will convert into a simple voltage divider network. Now we will calculate voltage across these points using voltage divider rule. We will multiply this resistance with total supplied voltage divided by the sum of all series connected resistances. Solve this equation. Voltage across these points will be equal to 19.58 volt. With this specified polarity, positive terminal will be here and negative terminal will be here. Now this same voltage will be appearing across this network because of parallel connection. So we can say that the anode of this diode is connected to positive terminal and cathode of this diode is connected to negative terminal, and voltage difference between these 2 points is greater than 0.7 volt. So we can say that this diode will be in conducting or forward biased mode, and this diode will be having 0.7 volt across its terminal, which is known as forward voltage drop of silicon diode. Now we have voltage across the terminals of diode, and we also know that this diode is in forward biased mode. So we have to add dynamic resistance in series with this diode. We have included the complete model of diode in this circuit. Now we have to find voltage across the complete model of diode. Voltage across this diode terminals are 0.7 volt, which is known as diode forward drop voltage. And we have to find voltage across this 10 ohm resistance. If we succeed to find out voltage across this dynamic resistance, later on we will add these two voltages together to find out total voltage across diode. So we know that voltage across these 2 points is 19.58, and these two resistances are connected in series connection, so we can apply voltage divider rule to find out voltage across this resistance. But before that, we have to subtract this diode voltage drop from this supplied voltage. So in our case, the supplied voltage will be equal to 18.8 volt after subtracting diode drops. Now this 18.88 voltage will be appearing across these two resistances, and we have to find out voltage across this 10 ohm resistance. So voltage divider equation for this 10 ohm resistance will be 10 multiplied by 18.88 volt divided by the sum of both resistances. Solve this equation. Voltage across this 10 ohm resistance will be equal to 0.04 volt. After calculating the value of voltage across this resistance, now we have to add up these two voltages to find out voltage across the complete model of diode. That will be equal to 0.7 plus 0.04 volt. It will become 0.74 volt. So 0.74 volt will be appearing across the complete model of diode in this network. Move towards the last circuit diagram. In this configuration, the diode is connected between two voltage sources with two resistances. This voltage source is making this diode in reverse bias because the positive terminal of this voltage source is connected to cathode and negative terminal of this voltage source is connected to anode. So we will omit this left half circuit of the network, and we will focus on right half circuit of the network. In this case, the positive terminal of voltage source is connected to anode and negative terminal of voltage source is connected to cathode. So first of all, we have to determine either this diode is forward biased or reverse biased. So in order to do that, this diode have voltage difference across its terminal greater than 0.7 volt, and the polarity of supplied voltage is also in correct manner. So we can say that this diode is in forward biased mode or conducting mode. As we discussed earlier, this diode is considered as silicon diode. So it will be having 0.7 volt potential difference across its terminal, which is also known as forward drop voltage of diode. Now, after the confirmation of biasing of diode, we have to include the complete model of diode. In this model, this diode will be having a forward series resistance, which is also known as dynamic resistance. So we have to replace this diode with complete model. In this model, this diode voltage drop and dynamic resistance in series are included. We have to find voltage across this dynamic resistance. Again, this is a series network, and we have to find voltage across this 10 ohm resistance, so we can apply voltage divider rule here as well. For that purpose, first we have to subtract the forward drop of voltage from supply voltage. So remaining supply voltage will become 19.3 volt. And these voltage will be appearing across these two resistances. So we will apply voltage divider rule for this resistance. That will become 10 multiplied by 19.3 divided by 10 ohm plus 10 kilo ohm. Solve this equation, we will get the value of voltage across this resistance, that is 0.019 volt. After finding out the value of voltage across this dynamic resistance, the value of this voltage and this forward drop voltage will be added together to find out voltage across diode complete model. So diode complete model will be having voltage across it of 0.719 volt. So this was chapter 2 exercise problem number 2.10. Thank you. See you again in next video.